Thank you again for coming out today, and happy to talk about this paper. Um, so I'll talk about a topic that's I think very familiar with everybody, namely inference compute. Um, as of this past year, we've seen a lot of different approaches for scaling inference compute and improving performance on all sorts of different tasks. One of the early papers in this area was from Snell at Berkeley that focused on a couple of kind of like main approaches for just scaling out parallel compute and scaling out sequential compute for different tasks. The three main ones that they observed were best of n, beam search, and look ahead search. But since this paper, there's been all sorts of different approaches around extended reasoning, around different approaches for RL to improve the efficiency of inference compute. But for this paper specifically, we wanted to analyze one of the more simpler approaches of it, namely best of n, because with this approach, you can kind of just take it off the shelf. Doesn't require any sort of like sophisticated post training, and so we wanted to see just how much we can extend this approach towards improving better LM performance. And so even with this approach, we saw something that's been termed the generation verification gap, where a lot of language models are actually capable of correctly generating responses. They're not actually able to like verify which of their responses is incorrect. And so you see this as you continue to sample more and more from a single LM, where as you generate more and more responses, your coverage or your ability to actually like correctly answer a problem continues to close, and you even like reach 100% on a lot of these different tasks. But your actual ability to select from these responses, or your selection at k, continues to kind of like plateau beyond just using like the majority amongst all of the different votes. And so what we wanted to see is to what extent can we close the generation verification gap in this specific repeated sampling regime. And so we want to see maybe weak verifiers could help us out. And so weak verifiers are just any function that can score responses imperfectly, but provide some source of positive signal. And so two classic examples of this would be like reward models. You can see all sorts of different reward models on Reward Bench. Now there's even Reward Bench v2. And it's pretty meaningful to scale and improve these different models because it can be used for all sorts of different things, whether it's like annotating data for fine tuning, doing any sort of filtration for pre-training. These models have kind of a generalist purpose that can be used for all sorts of things beyond just inference compute in our setting. In addition to reward models, we also look at LM judges. And so we took all of the top scoring LM judges on Chatbot Arena and wanted to see just how useful it would be to take these LMs and just use them to grade different responses from a generator LM in this case. And so what we find is that the weighted verifier ensembles outperform any sort of naive verifier ensembles. So rather, if you actually know how to weight these different reward models and know when to value others over the weaker ones, you can actually get performance that outperforms. You can get performance that outperforms any individual LM, and you can also get performance that actually allows you to help close this generation verification gap on all sorts of different tasks in mathematical reasoning, in scientific reasoning, and PhD level reasoning with GPQA Diamond, and even just more generalist reasoning with data sets like MMLU Pro. The problem is to actually know this weighting, you actually need some sort of like supervised data. And so the problem is you'd have to actually like go through and annotate, hundreds, maybe thousands of different data samples, learn that, use those annotations to actually learn the weights for this ensemble, and then apply it at inference, which can be pretty costly and kind of unwieldy, especially at scale. So we looked towards some older versions in statistical machine learning, specifically weak supervision. For those who aren't familiar, it's an approach of different statistical methods that help you aggregate multiple weak and noisy labeling sources. So you could imagine, like, if you wanted to predict the weather, you have all sorts of different metrics that are useful for predicting the weather, like atmospheric pressure, humidity, like what was the weather the day before, how sunny is it outside, and all of these individual signals can be weak and kind of noisy, but like by aggregating them together and by taking advantage of their complementary strengths, you can get something better. So this was famously explored in Snorkel back in 2017, but it's since been used for all sorts of different labeling schemes, most recently towards like pre-training and post-training labels. And so what we want to see is, can we extend this towards the setting of inference compute when you have a ton of different samples and a ton of different sources for verification? So we decided to propose Weaver, where we take all these weak verifiers and try to lump them together and learn how to actually weight them in an unsupervised fashion. And so to do this, we have to combine a bunch of different weak verifiers using weak supervision and learn the optimal weights without any sort of reliance on these ground truth labels for actually, doing gradient descent or any other learning approach. And so this enables us to handle a bunch of different outputs from a bunch of different models. So these different reward models can be binary scores, they can be Likert scores, they can be floats. And so this allows us to take all of these different scales for these scores, learn how to combine them, even though they have different verification quality, and do all of this with limited labeled data. And this allows us to transform even like weak verifiers that are imperfect into a stronger ensemble that can improve success rate up to 27.8 above just using majority sampling or just single sample alone. And so how does Weaver work? The first step is actually scoring. So you have to go through and collect all of these different outputs from all of these different verifiers. You have to use these verifiers to score all of the different samples that are available and find which ones are most effective, because you need to actually see like which ones are lower quality, which ones are higher quality. And you can intuit this by seeing which ones are the outliers over the entire ensemble. It's kind of this collective intelligence idea where, if you have all of your weak verifiers agreeing in a certain direction, they tend to actually be pointing in the right direction. Oftentimes when you have some sort of split, you can like weight them according to kind of like known priors around their different qualities. And you can estimate these known priors using a very small sample or a very small set of annotated examples. For estimation, this is usually about like 5 labeled examples, but you can use that small set of labeled examples to extrapolate towards hundreds or even thousands of data examples by using that as your prior. And once you have this prior, you can then select and combine these different weighted scores to choose the highest confidence response amongst hundreds or thousands of responses. Because ultimately, when you've applied this best of n setting, you have so many different samples to choose from. All you need to do is pick one that is correct. And so you can allow scale to be to your advantage in this case. And what we find is that Weaver can beat these frontier LMs and even shrink the generation verification gap rather considerably. The two main numbers to focus on is this comparison of majority voting and the highest scoring RM to our actual approach. So we're able to actually exceed majority voting by about 14% on average. And we're actually able to close the gap with a lot of these frontier models and even beat some of these frontier models. We're able to get within about like 0.5% of O3 mini, which is kind of exciting. And even more exciting, we're able to get around 6%, within 6% of Oracle verification. So this means like if you were to just have a perfect verifier and sample best of n times, we'd be able to get within like 6% of that on average for these different tests, ranging from Math 500, GPQA Diamond, to MMLU Pro. And so there's a few different aspects for how we can actually scale verification compute. One is simply more generations. So this has been explored, in all sorts of different papers focused on best of n sampling or majority sampling. But you can also, increase the model size for the actual models being used for generation and the actual models being used for verification. You can increase the number of verifiers that you'd like to use, so that instead of relying on a single good one, you could rely on a bunch of worse ones or a bunch of good ones as well. You can vary the quality of those verifiers and see how that affects downstream performance. You can even vary like the model family, so you can use a bunch of llama models, a bunch of gemma models, a combination of both, and all of these different aspects of diversity can have like interesting downstream effects on the quality of that ensemble. We see that like the best cases tend to use as many complementary models as possible just to leverage their different post-training strategies, their different data annotations that were used for post-training, and all sorts of different things. And finally, you can actually moderate the actual inference compute, so the actual number of flops that you spend towards generation verification, and get different variations to inference quality. What we find is that scaling generations continues to boost performance with Weaver, so that's super exciting. As we scale by binary factors, we can get better and better performance, at least up to 1,000 examples, which is what we explored with this original study. And this gap continues to close with the actual Oracle verification, that top dotted line on these graphs, and allows us to even go beyond O3 mini for some of these tasks like MMLU Pro. I think what was most exciting about this is that you could continue to scale compute, and like while there was diminishing returns, you continued to see better returns, and so like there was a value towards continuing to push inference compute. in this setting. Something that was also exciting to see is that like you could do this with models off the shelf. So you didn't have to do any sophisticated post-training, any sophisticated like fine-tuning to actually get this behavior. The models were actually capable of this reasoning behavior. They're actually capable of this verification behavior. They just had to be correctly aggregated and correctly utilized. We also found that the Weaver helps reduce the gap between these different model classes. So it helps you close the gap between 8B models and 70B models. It also helps you close the gap between 70B models and frontier LMs, specifically frontier closed LMs like O3 Mini. And what this allows us to do is basically leverage our compute more, especially in resource-constrained settings. So you can imagine, if you're on device, or if you're using, older hardware and can only run, like, say, like 8B models, you could get away with just using 8B models sequentially and eventually be able to close the gap with 70B. It would take you longer and it would take you more compute, but it would be able to help close that gap with 70B models just by throwing kind of like more flops at the problem. Same goes for going from 70B up to frontier LMs. You wouldn't necessarily need to spend on those frontier LM credits. You could just keep applying these 70B models, and ideally, with enough scale, you'd be able to help close that gap. And so these gains are pretty considerable. Like for the 8B models, we're able to improve performance by about 13%, give or take, and with the 70B models, we're able to improve about 14% and help close that gap. We also see kind of continued benefits from adding more verifiers, up to a certain point, I'd say. So the sweet spot tended to be around 4 to 6 verifiers, depended on the task and depended how we scaled the verifiers themselves. But for this x-axis graph, we were focused on basically adding verifiers in order of actual success. So like if you had some notion a priori of like which verifiers are better and which were worse, you could actually like continually add new verifiers and see basically how that affects performance. And so what we found is that by using like the top 4 to top 6 best verifiers, you're able to increase performance rather considerably. Obviously, this is like an Oracle setting in which you kind of like have this knowledge a priori, but it shows that like if you actually are aware of like which LMs are better for verification and which are worse, you can get these gains without going up to like tens of verifiers. You can do this even with like a small set of like 3 to 10. And so that was interesting to see. We also see that it actually improves the accuracy compute performance trade-offs. So we wanted to explore like with a given like flop budget or a given inference compute budget, like what's the highest success rate you could get when combining the inference compute for generation and verification. And so we're able to get improved performance with Weaver. But the problem is it requires more inference than just like running majority sampling, right? Because you need to do all of these generations, and then you actually have to then do more forward passes for your verification models. And so what we wanted to see is how we could like reduce this gap even more by finding some ways to like distill these verifiers down into a single model that kind of captures the strengths of all of these different verifiers. And so we explored a new form of like distilled verification called Weaver distilled, in which we took all of these different verifiers, used the Weaver annotations to actually then fine-tune a smaller model at the scale of 1 billion to 500 million parameters, and actually get pretty solid performance. Here's kind of a diagram of how it works. For actually training this like Weaver distilled model, you run all of these different RMs, you run all of these different LM judges, use Weaver to aggregate their scores, and then use these predictions from Weaver to then distill the model and condition on the instruction plus LM generation. So given any kind of LM instruction and the generation from that LM, Weaver distilled can then score it and then use that for actually doing the verification process. And so this allows you to skip on the process of running all these verifiers at inference or in some sort of like online setting, which can be really useful. And finally, we see that kind of distilled Weaver can capture up to 97% of the accuracy gains with only 99.97% of the compute, which is really, really cool to see. It helps push out the Pareto frontier in terms of this optimal balance between generation quality and verification quality. It takes some scale to actually get it to be successful. So you need to be able to fine tune on like thousands of examples to actually like get it to this level of performance. But what's nice about Weaver is because it's all like synthetic data, you can actually just scale it pretty quickly and then see how you're able to improve performance as you add additional queries. And so the main kind of like value of this approach is that, again, in these online settings, you can now employ verification much more cheaply versus running all of these different verifiers in an ensemble. As next steps, we're super excited to kind of like complete this generation verification loop. We're working with folks at Meta to fine tune and post train interesting models that allow us to improve the generation quality without having to go to verification again. So that's really exciting to see how we can use gRPO with the latest RL frameworks to actually push this out. We're also interested to see how we can make more compute-aware optimizations for these generation budgets. So how you can actually be thoughtful about how you actually select the generation budget and select the verifier budget for these different tasks, because it's not the same across tasks. Some tasks need more generations, some need more compute spent on verification, so that can be a tricky trade-off to straddle. And then finally, we're interested to see all sorts of different approaches for off-policy generation and verification. So how can we best teach generation and verification to other LMs that aren't necessarily specialized for that or aren't necessarily like prepared for handling that? That can be really useful as we try to generalize across tasks and as we try to handle new domains that don't have Oracle verifiers, which can be really tricky to actually post-train and scale performance on. But yeah, we're super excited by this project. If anybody has any questions, if anybody's interested in chatting more, please grab me after this. But yeah, thank you so much for your time. Yes.
Good morning.
Good morning.
Good talk.
Thank you.
First of all, I always like these approaches generally because it's how we learn as kids. You want to learn, differentiate, you can understand, and talk to your friend. Friends understand you tonic habit. That is what we're going to use. Kind of what my question is, can I use this in smaller, outside the developers of the LLMs, like in my business? So as an example, I want to train an agent to do. Thank you. Thank you. Good morning again. I want to train an agent to do market analysis. Now, any given type of market for any industry, if you go out on the web, very small subset. But if I take 100 different industries and I do show the LLM, the various kinds of analysis that are available that verify market sizing, can I get to the same point as having one big bunch of data? I mean, is it really applicable to my need as a business person?
Yep. Yeah, no, I think that's a great question. I think it can be advantageous to kind of have this like ensemble approach that you're describing, where it's like you have a bunch of different like LM agents kind of working on this different task, and they each kind of specialized towards these different aspects of the task. I think something that we found with this paper was that like it can be like the trickiest part is that aggregation stage. And so knowing like what's the best mechanism for that aggregation can be really useful. For us, we found that aggregation to be like weak supervision. So this like statistical weighting, and this statistical modeling of the different relationships. But for something like that, I'm curious to see if it would be, something as direct as just like, having all the LMs like collaborate in some sort of sense, like have some sort of like fusion of their responses or have some sort of like deliberation between them. Because there's been like a lot of papers that have shown that like even something as simple as like these like multi-turn debates or these multi-turn deliberations can be like super powerful. I'd be curious to see, like if that's the approach or if it's just like better verification, like more stringent verification for something like market analysis. That would be the strategy. So, like to I guess answer your question, like I think the two places where I'd see the bottlenecks are like the actual verification to make sure like it's the factuality and like the actual like accuracy of the responses are good, and then that actual aggregation stage to so how to actually like synthesize all that information. Yeah.
Hello. I have a question regarding the verification or the verifiers. So you showed a plot that was like number of verifiers by performance. And I think the sweet spot was 4 to 6. How much does the quality of the verifier affect like the number of verifiers in an ensemble?
Yeah, that's a great question. So what we found is like we see this kind of like U-shaped curve for different tasks, like not just the ones plotted here, but also other tasks that we've explored in the paper, where like quality is like becomes especially important, like basically the less and less verifiers you have naturally, right? Because there's less like they kind of have like more market share, so to speak, and so like you need that quality to be higher. And so that's why you see, like when we plot it from like best verifier to worst verifier on the x-axis, you see this nice curve because a priori, like these are the best verifiers. If I was to like plot this like randomly, like if I was to just like randomly sample amongst the 30 plus verifiers we tested for this, it'd be a much more like choppy graph. And so you wouldn't see as like nice of a curve. And so that's why we think like the aggregation and the actual like kind of like filtering and like weighting is so important, because otherwise like you have no like nice way of like actually extracting the value and actually being able to like get rid of the verifiers that are like not providing value and even being like almost adversarial in terms of like providing value. So it's super important. I hope that answers your question. Yeah.
Yeah, my question's a little bit related to that, but early on you had a slide comparing the like Weaver ensemble compared to frontier models. I was curious if you looked at if that was very sensitive to the task. Like in some tasks, maybe the gap is very small, and some gaps is very big, or it's pretty consistent across different tasks you looked at.
Yeah, I'd say the gap was pretty varied depending on the task. So, for example, like I think for GPQA Diamond, we saw like one of the biggest gaps, and that was most likely because just the nature of the task. Like it was PhD level reasoning, and like in physics and biochemistry and biology, and so as a result, like these LMs were just performing poorly just because they hadn't been like post-trained and didn't really have much knowledge or weren't best suited for these kinds of tests. We saw the gap tended to be smaller and more easily reducible for something like Math 500. One, because we think these LMs are kind of like saturated on this task, but also because there's lots of nice verifiers for this task. So there's lots of RMs, lots of reward models, and also lots of LM judges that are like specifically good at like math. And so that allowed us to close that gap much more easily. I think something we found to be like a nice avenue for future research from here is just like better verifiers and like more domain specific verifiers. So like having a verifier that's more specifically solid for like scientific reasoning, or a verifier that's really good for like coding. That could be a really powerful way to spend more compute and more resources, and something that I feel like is immediately generalizable, assuming you have enough data. Yeah.
Thanks. So I know that it's not part of the talk, but you mentioned it as the next step, like doing RL on top of this result. Do you think this result will still apply for RL? The reason I'm asking, because recently we found some, let's say, counterintuitive results about RL. You can apply RL just optimizing a random reward, and you'll still get like improvement on the model. So I'm just thinking maybe for RL, you don't need really to have like better verifiers.
Yeah, no, that's an interesting direction. I saw that paper as well. Unfortunately, I haven't read it as much, so I'm kind of curious to see like just how effective it is and just how generalizable it is. I still think there is a value to like better verifiers, even for just post-training more generally, because like while it might not be necessarily like essential for RL, like you might be able to get away with like a weak verifier or like even like a bad verifier to actually scale performance. It can be really useful for like data labeling, for any sort of like pre-training filtering of data, for other kinds of inference compute, and so we still think like it would be useful to like continue to explore better verifiers in that setting. More specifically, if it's like needed for say like GRPO, or if it's needed for like DPO or like other variations of RL, not as sure. But that's something we're like actively exploring right now, to like see basically how much we can like leverage that. So far the results have been good, but kind of curious to see now if like a random verifier would do the same thing. Yeah.
Hi, John. Great talk, by the way. On one of the like initial slides, you had talked about what models you used.
Yep.
You used the chatbot arena models and also rewards. did you explicitly compare the two on using verifiers from only LM judges and only reward models, or did you use a combination for all of the tests?
Yeah, so we explored these isolated settings that you described, where we like just use reward models or like just use LM judges to see like where we derive the most value. We found that for like the math tasks, so Math 500, the reward models kind of captured most of the value. Like you could get most of the performance gains from just using those reward models. And I think it comes from the fact that these reward models were like specialized for math. So you see a lot of the different top ranking reward models on Reward Bench are just like specifically for math and specifically process reward models for math. We found the LM judges who were particularly useful for more like general scientific reasoning, so like stuff like GPQA Diamond and also MMLU Pro, just because one, they were bigger models, so a lot of these reward models are 8B in size, but these LM judges are like 32B to 70B, and they were just better for that generalized setting. No. Yes.
Generic question. How LM judges works? Is it the same like ChatGPT model or it's specialized?
Yeah. So to repeat your question, what is the actual like setting, or like how are we actually using these models off the shelf? And it's super simple. Like we just take like say like a Llama 70B and just prompt it as a judge to take in the instruction, take in the response, and then use chain of thought to basically grade the generation. Yeah. And so we do that for all of them. Yeah. For all the LM judges, that is. Yeah.